We have a really good session coming up. 3 speakers all talking about potassium fertilization. As many of you know, there are some fairly large areas across the state of Minnesota that are test fairly low on potassium. And with record potash prices, I think there'll be a lot of interest in these 3 speakers. They all represent a different philosophy on how to use the soil test, and representing North Dakota, Iowa, and Minnesota. So our first speaker is Dave Franzen. He is a professor of soil science and extension soil specialist at my favorite place, NDSU. He has, to me, a very unique background in the fact that he was in the fertilizer industry for 18 years in central Illinois before coming on staff at NDSU in 1994. And one of the very early pioneers in the United States for considering clay chemistry and formulating potassium recommendations. So David, thank you so much for being here today.
Thanks very much. So I'll use this, and are we doing okay with this? Can you hear? Okay. All right. I'm glad you have people. So I'm the chair of a soil testing, regional soil testing committee workshop in Coralville, Iowa. So as soon as our session is over, I'll be taking off. But I'm already getting questions about whether it's going to be offered remotely, and the short answer is no. But then I look around the room here, and you got you and Anthony, and it's expensive to do this. And so those at home that aren't going to brave the roads like I am, I hope you appreciate this. So anyway, what my introducer said about a pioneer, you'll learn shortly that that's not true at all, and I'll give credit to whoever credit is due, but that's fine. So if you took soil fertility, show hands, anybody take soil fertility? Did you have more than one day on potassium at the end of the semester? Did you have 10 minutes?
It was 30 years ago.
Well, I remember, and it was Fred Welch, and it was 15 minutes of potassium and like 2/3 of nitrogen, and like it's easy, right? You look at the book, this is what they say. Available pool is a potassium on the CEC, solely available pool, potassium and clay interlayers, and unavailable pool from minerals like feldspars that maybe you'll get some good out of 3 generations from now. So that's all wrong. So go home and cross this out of your book. So I kind of finished a lot of my work on nitrogen around the state, and we were pretending to be Iowa in the southeast part of the state, change of rotations from wheat and different things that don't really remove a lot of potassium to corn and soybeans, and sometimes soybeans after soybeans, I'm sorry to say, for over 20 years. You can imagine the amount of potash that is removed when you go to something like that and don't change your fertilization systems. And so in the southeast part of North Dakota where we did our work, our soil tests were anywhere from actually below 100 to maybe 200. And 30 years ago, looking back on the records, they were 500, 600 ppm. And people just thought it would be that way forever. All right, so I work with Alma Chatterjee, who's down in Ames now with USDA ARS, and Manbir Rakar was a master's student, and she went on and got her PhD, and now she's working at Montana State with their very acid soils in that state that they have to contend with. And so anyway, I just simple studies, K rates, and I figured it would tend to show us that our 150 part per million critical value recommendation was right about 80% of the time, and life will be good, and I'll move on in a couple of years. And so I looked at the data, and like half of it didn't. There were some that tested high that we had a really good response to, and some that tested really low. We didn't see a hint of response. I'm like, what the heck? So lots and lots of studies between 2014 and 2016, and half the experiments turned out opposite what we expected to. That the high testing sites many times would respond and get very, very nice yield increases, 20, 25 bushels sometimes. And you had K-test down 60 part per million, thought it would be a slam dunk, and we didn't see a hint of any kind of a yield increase. And so that was really puzzling. And I think I'm a pretty good researcher, and I don't think I screwed things up. So I went to an ASA meeting, which is always a good thing. And I sat in a session on potassium on purpose. You know, the leadoff speaker was Don Sparks, who's actually the expert in this kind of thing. And I'll show you why he is here in a minute. He didn't start off to be an expert in it. He worked out in Delaware on some really sandy soils. And so he thought, just like I did, potassium simple, that's what they say in the textbook. I'll put on rate experiments on corn, alfalfa, some other crops, and we'll get some kind of critical value. And what they found is on those sandy soils, he didn't get any response at all. And he worked for 10 years on them, didn't get any response at all. And so he's a way better chemist than I am. And so he started digging in. And so he kind of looked at what the soils are made of. Very sandy, the CEC there in the middle. On the one side, the CEC is what, 4.4 to 4.8, and 4 to 5.8. The clay minerals are various, and it just seemed like, why in the world am I not getting any responses? And then he kind of looked at where the potassium was in all of that mineralogy, and a lot of the potassium was in the minerals. It was in primary minerals, the feldspar, not so much in the mica. Exchangeable K was minute, which is reflected in the soil test. Exchangeable K had some, but that primary mineral K kind of caught his eye. So the total K contents of sand fractions were very, very, very high for everything that he went with. It turns out that his sand isn't quartz. His sand is largely feldspars from the runoff off the Appalachians, over the millennia. And so it's not quartz sand like, we think of in the beaches of North Dakota, for example. So if you're a pretty good chemist and understand what the dissociation of minerals to solubility or anything that becomes soluble, there's a constant in between the different phases, and that dictates, well, it's a reflection, doesn't dictate, the numbers dictate what the K should be. But once you get the K, then it kind of gives you an idea about how strong that dissolution is, from the K mineral to the K non-exchangeable to the K exchangeable to the K in soil solution, and then uptake. So there's adsorption and desorption, and they're not the same. So a lot of, well, he sent me this slide presentation, but a lot of this is in the chapter in the old PPI book about potassium in agriculture that most soil fertility people skip by, because it gives us flashbacks of our soil chemistry course, and so we tend to skip that when we move on. But he identified all this stuff back in the 80s, and we were just too stupid to pay attention to it, apparently. So we think of non-exchangeable potassium, and that's the potassium in between the clay layers and smectites normally. And we think of it as not really very, very soluble. It doesn't really flow out of the minerals very easy. But this showed that over a period of time, there was quite a bit. There was quite a bit of potassium released from this non-exchangeable pool. And from the sand fractions, from the feldspar, there was a lot of potassium released from that as well. So it's not as, so this is potassium feldspar. I'll show you the clays here in a minute, but potassium feldspar is just a series of tubes, really. And just like clays, they have isomorphous substitution during the crystallization. I'll show you a little bit of that here in a minute, but so it has a negative charge, and the negative charge is satisfied by potassium, just like the negative charge in a mica mineral is satisfied by potassium. And so it kind of acts like a clay. And so it's almost like a non-exchangeable K in a way. Um, and so it's just chock full of potassium, and of course it can leak. So it leaks. So the new textbooks, when they come out, are going to look something like this. It's not going to be 15 minutes at the end of maybe soil fertility thing, but I think the person should probably spend a week on it, because we have the potassium inputs on the upper right there. We have erosion and runoff losses. Those aren't trivial, especially in North Dakota. You can actually make an illite from a smectite if you pour the potassium on it. And when you suck the life out of a smectite or an illite, then you can make a smectite. It can go back and forth between the two, and maybe show you how that happens. You get potassium from the feldspars and from the micas. It leaches from our sands. The plant takes it up, you harvest part of it and ship it off to Korea or someplace. But you also have unharvested plant parts. And so one of the things you see is that you might soil sample directly after a corn harvest, but then it rains after that, and the potassium in the stalks just leaches right back in the soil. And so you're not really picking that up. So it's complicated. It's complicated. Nitrogen is complicated because of biology. Potassium is complicated because of physical chemistry. So I walked out of that seminar. I walked into the seminar thinking I know a lot about potassium, and I walked out of the seminar thinking I don't know a darn thing about potassium. And so it was humbling, and I'll just share that with you. It's hi, my name is Dave. And yeah, I thought potassium was simple. So we measured. I did a survey in the state because I really had no idea about. Well, I kind of did, but not really. So we took soil. I took soil samples from every county in the state, and I took the archive samples from all of our studies that we did in the southeast. That's the first thing. Smectites, hillites, kaolinites, chlorites. Sent them off to a lab in Ontario for an ungodly $400 and some a sample. And because smectites we know will fix cake. Fix is horrible name. It's more like temporarily retained. And illites don't temporarily retain potassium. And so kind of needed to know what was going on with that. I thought maybe that might be important. So here's a short course on clay chemistry. So clays aren't just little bitty particles. They are crystals. They originate from the mineral mica. If you pick up a piece of granite from some till-plain soil someplace, and you look at it, those shiny flat pieces that are embedded in there, that's mica. All right, that's the original. Those clay sheets have potassium that holds everything together. But clays are made of sheets of silicon oxide, and there's a depiction of it. And they're made from sheets of aluminum hydroxide, and they're kind of sealed together covalently, I think, because the oxygen kind of partial tie to the OH group on the aluminum hydroxide. So that's a 1-to-1. Like if you have a kaolinite, and there is some kaolinite in the state, everybody has kaolinite because wind blows around. So that's a 1-to-1. One sheet silicon oxide, one sheet aluminum hydroxide. These form from the magma inside the mountain of Mount Doom, if you're a Lord of the Rings person. Anyway, so in the condensation of these things crystallize. And so this is how they crystallize. And you ask yourself, well, why do they do that? So I'll give you the same answer my physical chemistry professor at Illinois gave me when somebody asked the similar question, and he turned around to the class in one of his rare moments when he actually talked to us and said, because it has to. So these things coalesce like that because I have to. So back to the board. All right. So then a 2-to-1 clay like smectite illites, that's a sheet of aluminum hydroxide in the middle. And then on the top and on the bottom, you have a sheet of silicon oxide. So that whole thing is a 2-to-1 sheet. And then those sheets are stacked on top of each other with varying degrees of separation between the 2-to-1 layers. And the degree of separation has a lot to do with how much potassium is in there. During its condensation from the fires of Mount Doom, we all think of nature as perfect. And this might be a newsflash to you, but nature is never perfect. And so during this period of time, there's not just silicon and oxygen and hydroxide and aluminum floating around, but there's magnesium, there's aluminum, there's all kinds of stuff. And some of it, because of the size of the atom and its shell, can substitute. And so this happens in the silicon oxide sheet. Aluminum, which is a +3 charge, substitutes for a silicon +4, and that gives a net negative charge. You've lost a positive, haven't you? And the same thing happens in your aluminum octahedral, and magnesium, which is a +2 charge, will substitute for aluminum, which is a +3, and so there's another negative not satisfied, and so that's the source of the negative charge in clays. So that's the simple version, but that's how it gets there. All right, so I've thrown these around a little bit, and so I want to do due diligence to look at that laser pointer. My grad student taught me this. All right, so here in the center, let's start in the center. Sometimes I start in the left and I lose people. So if we have a mica mineral that's gone through a weathering process, it's lost some of the potassium from the in between the 2-to-1 layers. And so what we have is something we call illite, but it's also called hydrous mica, or sometimes weathered mica. And that's exactly what it is. You can see the clay sheet right here, and then a little dimple, and then a clay sheet, and a little dimple, and a clay sheet, stack, stack, stack. Potassium in the middle, but it's lost some. Dimple, that's what that is. It's lost some potassium, but this is still chock full of potassium. And so in our soils, what I think I see is that it supplies potassium whether it's wet or dry. Doesn't care whether it's wet or dry. It's just so chock full of potassium that it just kind of oozes out over time. Smectite is the next weathering product. And it's lost most of the potassium in between the layers. So the layers have a greater distance in between the layers. When it's moist, water will flow in and out along with the ions. But when it's dry in July and you think your soil test is enough to carry you, it collapses and it traps the potassium inside. And I think that it acts like a kind of a semi-dry sponge you put on a table that has a little puddle on it, and it draws the water into it along with the ions. And so not only I think is it trapping it, but it's also taking back some of the potassium that might be out in the outside solution, because it is, when you have really high smectites in your soil, you think you're okay, and then it gets really dry in July and August, and you start to see those potassium deficiency symptoms. So that's that. This is kaolinite, 1-to-1, stack, 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 no shrink, no swell, really low CEC, because the only negative places that cations can stick to is just on the outer surfaces. It's not, see how wavy these are and how detached they are and how much cations change they could have. This is one level, and then this is another level on top of that. So you got the inner layer where the potassiums can come in and they can go out. And so the CEC in the smectite is highest, this is medium, and this is really low. Our kalinitic soils, West River, around Dickinson, for example, where I found 75% of the clay was kaolinite, the CECs in those soils, even if they're a clay loam, the CECs are only 12, 13, something like that, because of the clay type in there. So you think you're okay, you get to July, it's really dry, and your corn turns like this, and potassium deficiency. And sometimes you'll see it on soybeans, but you'll see it on corn first. So John Brecker, who's now the main agronomist at Agriculturalist or whatever at AgVice Labs in Northwood, he's my student that did this, and he's pretty close to a genius. And So anyway, he used the kind of clustering techniques that we use a lot of times in precision ag to kind of sort out what ratios of smectite to illite things divided out, if they divided out, and he found they did divide out. They divided out when the smectite illite ratio was 3.5. So you graphed it out, and what he showed is that when we started to look at that smectite illite ratio, it was far more instructive, not perfect, but far more instructive about what kind of responses we're going to get. So when the smectite illite ratio was less than 3.5, the critical value was 150 ppm, just like it was. And if it was greater than 3.5, then the critical value went up to 200. So that's what we base our potassium on. Our yield increases to potassium are not as great as what you would think they would be. And I think that's mostly because of the amount of potassium feldspar that we were working in. We're in the southeast part of North Dakota, around this area roughly. And so the potassium feldspar in that part of the world is about 15% of the total mineral matter. And so I think that's why we only saw 25, 30 bushel yield increases at the most, is because the potassium feldspar is also leaking. So at an expense of $60,000, I got a survey of the state done. Everything East River had at least 3 sites within the county, 3 major soil groups, and West River 2, because I didn't think they'd want to be Iowa. But I gave a presentation on soybeans out of Dickinson the other day, and so maybe I'm wrong. But I think we were very lucky. We just got lucky because we worked in this area here, which had significant number of sites that were low smectite and significant number of sites that were high smectites. If we would have done it, say, up around here in Grand Forks, I don't think we would have seen it. If we'd done it out here, we wouldn't have seen it. And so I think we just kind of got lucky. Lucky's good sometimes. So here's our critical values for corn, alfalfa, 200 ppm. If it's over 3.5, if it's less, 150. Beets and spring wheat are also in there. Almost every crop I've put something in there. So also developed a North Dakota nitrogen calculator for corn, just for corn, and it has a picture of the map in there. The person can select what they are, what soil test level is, corn price, potassium price, just like the nitrogen calculator. And you get and then in North Dakota, and this doesn't happen in Minnesota, but we have salts all over the place in North Dakota. And so putting on too much potash, it adds additional salt. And so once we got to 200 pounds of 0060 an acre, the yield tailed off. And so we don't recommend any more than 200 pounds of 0060 in any given year, just for that, so put it on each crop, but don't overload the corn. We also have a circular about how it impacts crop potassium nutrition and tillage systems. That goes into even more detail than what I shared today. So all soil fertility is local, and I believe that sincerely. But if you want to visit, there's my information, and thank you for your time.
Question on the screen.
Oh yeah, okay. Other soil testing methods. Yeah, so John Brecker, my amazing master's student, he did the wet potash test that Iowa uses, and it wasn't nearly as good as the dry. He used the soil test that never dies. The percent base saturation. I don't know why that doesn't die, but it doesn't die, and it wasn't as good. And then he used he developed a resin extraction. We thought maybe that would be helpful, and it was horrible. And then he did 2 different extraction times with sodium tetraphenyl borate. I think that's, yeah, I'm pretty sure. And that didn't do as good. So at the end, the dry potassium test with the clay chemistry considered was the best solution. Anything else? Thank you.
Give Dave a hand.